Hello and welcome. These are the solutions to Quiz 41. So Quiz 41 is going to get into the topic of molecular orbital diagrams. These base diagrams are given on exams for B2, C2, N2, and any ions of these elements on the left side, and then O2, F2, neon 2, and any of their ions on the right side. Now notice that what's being shown here are the 2s orbitals of these atoms and the 2p orbitals of these atoms, showing the relative energies of their orbitals once we consider their relative energies. So our scale is energy increasing. The 2s orbital is the most stable. We get the most stable orbital for the sigma 2s. Then the anti-bonding orbital, the sigma star 2s, is higher in energy. So we get an orbital that goes down in energy, then an orbital that goes up in energy. So then we have a pi set of orbitals. We get the pi 2p orbitals. These are the combination, or if you think of even the s orbitals, just the combinations of electrons meeting up in the middle, nuclei in the middle, the pi 2p, or the vertical p orbitals overlapping to make a pi bond. And there's two of those orbitals, and they're degenerate, equal in energy, so that's why there's two orbitals here that go down in energy for the bonding contribution, then up for the anti-bonding. So we have the pi star 2p orbitals up here. And then the next orbital is the sigma. So the sigma is this orbital here. We get this overlap here. Now, the problem with the sigma orbital for the smaller atoms is we don't have a relatively high positive charge, and we already have electrons kind of in that same region. So it's hard to pack two more electrons in between the nuclei of atoms like B, C, and N, and B2, C2, and N2, because we don't have enough nuclear charge to sort of pull those electrons in. And so that's why this orbital is higher in energy than the pi 2p set of orbitals. So this would be our sigma 2p, and then up here would be our sigma star 2p. Now, this ordering is kind of, not exactly something you may have predicted, but it's something you can understand and then interpret from a diagram that's given to you. Then for O2, F2, neon 2, and their ions, we saw the 2s orbitals, the 2p orbitals. Here, the big difference is that you still have the sigma 2s, the sigma star 2s, but then the sigma 2p is lower in energy. So when we're thinking of an atom like oxygen and its nuclear charge, and we're thinking of, we have some electrons here making the sigma 2s orbital, then when we're thinking of the pi orbital, or the p orbitals making the sigma overlap, we have enough nuclear charge to sort of pull those electrons into a stable or more stable orbital than with B2, C2, N2 and their ions. So the next orbital would be the sigma 2p, then the pi 2p, then the pi star 2p, and then the sigma star 2p. Just remember, sigma is the case of bonding that's symmetrical about the bond axis of the molecule, and then the pi is symmetrical about the plane of the bond. So it's like a planar type bond. Okay, so the issue for something like C2 is to use the proper diagram to think about the proper number of electrons. So each of the carbons would be a 2s2, 2p2. So we might think of having this set of electrons here, and then these electrons pair up in the middle to make C2. So you have one carbon atom here, another carbon atom here, then you imagine those carbon atoms overlapping their orbitals to make a sigma 2s, sigma star 2s, pi 2p, apply Hund's rule, and then spin pair the last two electrons in. And so C2 would look like, from the MO diagram, a molecule that has a total of 6 bonding electrons minus 2 anti-bonding electrons. So we have a total of 4 net bonding electrons. So 4 net bonding electrons is a double bond. So what we're going to do is multiply this by a half to calculate our bond order. So our bond order is 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. So if you think about a single bond between, think of a different molecule. Think of hydrogen. 1 electron, 2 electrons. So a single bond contains 2 electrons and has a bond order of 1. So the bond order of a single bond is 1. So the bond order of a double bond should equal 2. And so our bond order for C2 is equal to 2. So we have a double bond between the carbon atoms. And then the anti-bonding electrons cancel out a bond. So these two electrons here are sort of what you might consider to be non-bonding electrons. Whenever you have a bond cancel out with an anti-bonding orbital, that's just going to result in a pair of electrons on each of the atoms on average. So C, double bond C, because we have a bond order of 2, is how we get there. And then lone pair from the bond canceled out with the anti-bond. So the net issue whenever you have bonding and anti-bonding canceling each other out is non-bonding pairs of electrons. And so from the MO diagram, the most consistent Lewis structure would be one that looks like this. So you can kind of come up with a Lewis structure from an MO diagram by thinking about the bond order and the unpaired or the lone pair electrons canceling out from the anti-bonding electrons. Let's look at another question, number 2. Which statement is true for the molecules or the ions C2, 2 plus, C2, C2, 2 minus, O2, O2 minus? Okay, so for these ones here, like if you imagine taking 2 electrons off of C2 to go to C2 plus, and we're going to take the last 2 electrons out. So we're going to take these 2 electrons here away. It'll be hard for me to erase those, but we're going to have the pi 2p now with just 2 unpaired electrons. And so anytime we have 1 or more unpaired electrons, then that molecule would be paramagnetic. It would be pulled into a magnetic field. So C2, 2 plus, paramagnetic. C2, though, had all spin paired electrons, so that would be diamagnetic. Diamagnetic molecules or atoms are not pulled into a magnetic field. You might think of it as meaning they're not really magnetic. So paramagnetic pulled into a magnetic field, diamagnetic is actually weakly repelled by the field, but that's just the case whenever all the electrons are spin paired, it's not being pulled into the magnetic field. C2, 2 minus, we have now 2 extra electrons. So imagine C minus, C minus, that would be a 2s2, 2p3 atom coming together on each side to make C2, 2 minus. So it's like what we're doing there is we're adding an extra electron to the mix, and then it would go in the next higher orbital in terms of energy, and still spin paired. So that ends up being diamagnetic as well. O2, we got to use the O2 diagram. So the one way you might think of O2, and to sometimes simplify this, might be to think number of electrons of O2, 8, that's not even right. It's 6 valence electrons each times 2. So 12 valence electrons. So we're just putting in 12 electrons in for O2 over here. So 2, 4, 6, 8, 10, and then apply Hund's rule, spin pair those 2 electrons in the degenerate orbitals so that you see that their spins are paired, and then O2 is paramagnetic. Now O2 is truly paramagnetic, and it really is pulled into a magnetic field. If you just look at a Lewis structure of O2, you would probably not predict any of these electrons to be spin unpaired. So that's the Lewis structure of O2 doesn't really tell us everything we need to know about O2. So O2 is actually paramagnetic. We pick that up from the MO diagram. Now if you go to O2 minus, you add 1 more electron. So O2 minus now has 13 electrons. We add 1 more electron. We still have a net unpaired electron. We still have a paramagnetic molecule. And so all of these are paramagnetic except for 2. And the 2 that are not are C2 and C2, 2 minus. So 3, an important feature or important property of molecules is the energy difference between the highest energy molecular orbital occupied with electrons, that's sometimes called the HOMO orbital, and then the lowest energy molecular orbital unoccupied with electrons is called the LUMO. Okay, so it's asking us to identify the highest occupied molecular orbital of N2. Well, N2 has 10 electrons, because each of the N's has 5 valence electrons. And so N2 also has the same number of electrons as C2, 2 minus, because that also has 10 valence electrons. And so it looks like the diagram I already have over here for C2. And so for C2, 2 minus, that we already have shown, that's going to match for N2. And that highest occupied molecular orbital is the sigma 2p. So sigma 2p is the highest occupied molecular orbital for N2. Then we can also rank bond lengths with an MO diagram. Like for F2, if we throw in all the electrons for F2, that would be 14 electrons. So we need to add 1 more electron, spin paired. The bond order for F2, what we might do is calculate for these molecules, what are their bond orders from the MO diagram? And then for F2, we'd have a total of 8 bonding electrons minus 6 anti-bonding electrons times a half would equal 1 for a single bond. Now that's the same basic Lewis structure we would have written for F2. So we kind of get a diamagnetic molecule, one single bond between the atoms matching with what we expect from the Lewis structure. For N2, the previous example we were looking at above has a total of 8 bonding electrons and then minus 2 anti-bonding. In fact, from this MO diagram, it's going to be impossible because this anti-bonding orbital here to ever have a bond order greater than 3. So N2 is going to end up with that triple bond order of 3. And so that looks like this, and then the anti-bonding electrons that had canceled out give us the lone pair. And then for B2, we have this diagram over here. We have a lot fewer electrons. We'd only have 6 electrons going in, so we'd have 2, 4, and then in the pi 2p, we'd have these 2 unpaired electrons, just like C2, 2+. So B2 would look like C2, 2+, and would have a net bond order of 4 bonding electrons minus 2 anti-bonding, and then times a half. And that also equals a bond order of 1. So now the shortest bond here is going to be the triple bond of N2. So N2 is definitely the shortest. And so we can roll out these choices. So N2 is definitely the shortest. And then when I'm looking at B2 and F2, both of which have a bond order of 1, the way I can make this comparison is to think whenever the bond orders are the same between 2 atoms or 2 molecules, single bond versus single bond, the question becomes which of the atoms is smaller. And fluorine is a smaller atom than boron because it's further to the right. So the atomic size of fluorine is smaller, so the bond length of F2 is shorter than the bond length of B2. So we're going to go N2 to F2 to B2. So B2 the longest bond here because it's the lowest order, and then the biggest atom. So that's how we can use molecular orbital diagrams to answer a series of questions about things like the MO diagrams and Lewis structures and bond orders, bond lengths, and magnetic properties and orbital designations. Okay, number 5. In sequential order from left to right, what are the hybridizations best describe the carbon atoms in the molecule? So we're just starting here and describing this atom here. Trigonal planar, 3 domains is all I need to know that that's an sp2. So that's just coming from trigonal planar is sp2. Then I have another trigonal planar, so I have 3 domains about the next carbon, so that's sp2 as well. And then I have a tetrahedral carbon, so I'm picking up this is tetrahedral because we have 4 total domains about that carbon, so that's sp3. Then I have 2 sps. These are sps because we have linear bonds. We have 2 domains about each of those carbon atoms, so those are each sp. And then our final is an sp3 because it's tetrahedral as well. So we should predict this bond angle is 109.5 degrees. Not 90, it looks 90, but it's really 109.5. Remember, we want to be able to draw Lewis structures flat so they're easy to write, but then have a thought that the real structure of the molecule is going to be much more complicated. And so if we're thinking of the structure of this molecule, like you might be picturing it more like you have a carbon H double bond to a C, so you can start interpreting the structure in such a way that then you're just picturing these 120 degree approximate bond angles. And then if you want to kind of continue with the structure with this approach, you come up with something that looks like this. So the real structure of the molecule looks something that's more along the lines of this in terms of its 3-dimensional shape. So to answer the question, we go sp2, sp2, sp3, sp, sp, sp3. sp2, sp2, sp3, so it looks like answer A. Number 6. For each molecule below, give a Lewis structure, bonding domains, electron domain geometry. For carbon atoms with 2 to 4 total domains, determine the hybridizations of each atom, sketch the geometry, determine the molecule is best classified as polar or non-polar. ClF3, we've probably done this one enough times. And if you're not sure, just go through the proper steps to come up with a seesaw structure, because we have 5 bonding and 1 non-bonding, 5 total domains, 4 bonding, and then the molecule ends up being polar. And then, so SF2, 2 lone pairs on the sulfur, single bonds to the fluorine, not minus charges, 0 formal charges around the molecule. And so here we're going to have a bond angle of about 109.5 degrees. The structure is going to be bent. The ECl2, 2 plus 7 times 2, 16 electrons, so that's going to be a linear bond. So that's it here. So linear, 180 degrees. BRF4 minus, so that's going to be 36 electrons. That's going to be a central bromine with 4 fluorines and then 2 lone pairs. So this is going to be octahedral and a square planar. So square planar structure. Let's talk about the polarity of a few of these. Our 2 fluorines are opposite each other here. They cancel. These fluorines exactly opposite. They cancel this. So Br F5 or Br F4 minus is non-polar. Be F2 non-polar for the same reason. These bonds cancel each other out. So this molecule is non-polar as well. SF2 is polar because the fluorines are opposite, pulling away from the sulfur, so that's definitely polar. So the first 2 molecules are polar, the next 2 are non-polar. ICl2 plus, so that's 21 minus 1 for the charge for 20 electrons, and so that's going to be a central iodine, 2 chlorines with lone pairs, and that gives iodine 2 lone pairs. So this is a structure just like SF2. And so this definitely ends up being bent, 109.5 degrees, also definitely polar since it's not a linear molecule. And then for some of these organic molecules, we have propane next, so that's CH3, CH2, single bond CH3. So these are all tetrahedral, so all carbon atoms here are sp3 because they're all tetrahedral. All the bond angles here approximately 100.95 degrees. This molecule here, CH3. Some of these are just tricky, like if you go O and then CH3, like we can't get the proper number of bonds onto this carbon and that oxygen. So try this instead. So try putting the oxygen onto the carbon and the next carbon onto that carbon for CH3. And then just give the oxygen a double bond, 2 lone pairs. So then each of the carbons has 4 bonds, each of the oxygens 2 bonds and 2 lone pairs. This is the molecule acetone. And so for this molecule of acetone, we have sp3 for the outer carbons and then an sp2 for the internal carbon. You could describe the O if you want as an sp2 as well. And so then the bond angles of the central most carbon is 120, and then the outermost carbon is 109.5. And so the next molecule, CH2, double bond to a CH, so I get 4 bonds about the first carbon. And then we're going to another carbon, double bond to an O, single bond to an O, single bond to an H, lone pairs on the O's. So we have sp2 for all the carbon atoms. So we have sp2, 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 120 degree bond angles, trigonal planars, and an sp3O. Our last one has a nitrogen, so we have CH3, CH2, NH2, and so this molecule here would be sp3 for all of them because they're all tetrahedral and all approximately 109.5 degree bond angles. Let's address polarity for a minute. Propane, non-polar bonds. CH bonds aren't very polar, and even if they are, they're all kind of almost canceling each other out. So this molecule here we'd say is non-polar. Acetone, we have a polar group here that's not, has nothing opposite of it, so this molecule would be polar. The the carboxylic acid group, definitely a polar molecule here in the next, and then this group here is polar, nothing exactly opposing itself, so that's polar as well. Remember, for something to be nonpolar, you want the exact same atom to be opposite of itself in the entire structure. So something like CF4 would be nonpolar despite having polar bonds. We don't have anything directly opposing these atoms in these structures here, so J, I, and H are all polar. Okay, hopefully that gives you some help on this particular quiz. That's all for now. Thank you.